Bueno, ¿qué tal? Buenos días. Continuamos con el ciclo, ya sabéis, de seminarios de aquí del Instituto de Estructura de la Materia. Hoy le corresponde de nuevo al Departamento de Química y Física Teórica. Entonces tenemos a Gonzalo Olmo, que es un profesor de la Universidad de Valencia, y le va a presentar Fernando y su charla.
Vale, muy bien. No hace falta, no hay nadie que no entienda español, ¿no? Oh, you two don't, okay, so we switch to English. Okay, so it's my pleasure to introduce Gonzalo Olmo. Gonzalo got his degree in physics in Valencia and also his PhD in Valencia. Then he was a postdoc in Milwaukee and then Perimeter, and then he came here. He spent 3 years here working with us, so he knows the place very well. We know him very well. After that, he moved to Valencia, where he is now professor at the university. He's the department head, the head of the Department of Theoretical Physics. He has been, and he's the vice president of the Spanish Relativity Society, SEGRE. His work has touched different subjects, both in general relativity and alternative theories, modified gravity theories. And today he will be talking about the gravitational collapse and non-singular black holes beyond the Earth within this context of modified gravity theories. So, Gonzalo, please.
Thank you, Fernando, for the introduction, and thank you, everyone, for being here. It's a pleasure, again, as usual, to be here in Madrid with you, where I spent a few nice years, a long time ago. So, and today I want to fix this first, because I cannot touch anything otherwise, I guess. Well, I want to present some summary of several works I've been doing in the last years. They are all interconnected one way or another, and they all converge in this title, more or less. So, and this is the idea of gravitational collapse and how this could proceed in scenarios with non-singular black holes. Okay, we want to mix all these things. And an additional ingredient is that we will need dynamics beyond general relativity. Okay, so this was supposed to be a talk for a broad audience, not specialists in any particular subject. So the idea is this one. Okay, so probably most of you have already seen these two pictures. The shadow of a black hole, the accretion disk around a supermassive compact object in the center of a very far away galaxy. Okay, and this distribution of light around this object is compatible with our the traditional view of black holes in general relativity. Okay, and the other picture here represents the first detection of gravitational waves by the LIGO observatories. The two waves were observed, these two different waves were observed at more or less with a small delay in time, and when you superimpose the two, they fit well, so they represent the same phenomenon. And this is this illustrates the emission of gravitational waves by the collision of two very massive and compact objects, around 15 solar masses or so, I don't remember. So these waves are compatible with the expectation from general relativity for the collision of two black holes. Okay, so since these waves fall within the frequency range of acoustic waves, it is typical to represent them as acoustic waves. So we usually say that when we detect gravitational waves, we are listening to the universe. Okay, because of this analogy. And so we can now listen to gravitational waves and see black holes. So, and all this suggests that what we are observing is indeed black holes. Okay, but though these observations are compatible with our intuition of what general relativity should produce, the fact is that the black holes of general relativity have conceptual problems. And these conceptual problems are related to the notion of singularity, because black holes in general relativity are singular objects. They produce singular geometries, and this is a limitation of the theory that indicates that the actual black holes should not be exactly like those. The black holes of nature should not be exactly like the black holes of general relativity. So we need something different, something that avoids the singularity. Okay? So in some sense, I like to interpret these images with this analogy. So we have the silhouette of an animal that looks like a horse, and maybe if we could listen to it, it could sound like a horse. Okay, so the silhouette is this picture, and the sound would be this picture. The point is that if we look very careful to this animal, we're not very sure if this part here is another ear or is maybe a horn. So maybe it could be a unicorn. Okay, it's not exactly the expectation from general relativity, or could even be something even more exotic, like a zebra unicorn. Okay, so the fact that these observations indicate that there are compact objects that look very much like the predictions of general relativity doesn't mean that they are exactly the predictions of general relativity. So we may expect some modifications. Okay, and this is the motivation behind many efforts in the community to propose and analyze new kinds of compact objects, astrophysical compact objects, to find alternatives that do not have the problems of singularities in general relativity. Okay, so this is one, and all this idea of black holes in general relativity started with the first exact solution found by Karl Schwarzschild, and it is given by this line element, and the line element is like the DNA of space-time. Okay, so it contains all the information about that space-time, and if you have a quick look at it, it is quite evident that there may be problems when r is equal to 2m, because this quantity here vanishes, this gives 0, so it's an infinity. So there are problems, there may be problems at r equal to 2m, and also at r equal to 0. Okay, but at the time when this line element was discovered, nobody was worried about that, because this is a solution, this is a vacuum solution without sources. So the interpretation was that this was a valid solution outside of stars, spherical stars. Okay, and that inside the stars we would have a different solution that depends on the matter composition and dynamics of the star. Okay, so in principle this was not assumed to be valid around r equal to 2m or even r equal to 0. Okay, so everything was safe at that time, nobody worried about that. Okay, but when the first explorations of internal solutions were done, it became apparent very quickly that there was a limit to the amount of matter that we can put in a given radius. So the compactness of an object, of a star, cannot be an arbitrary thing. Okay, so in particular, if you consider a solution of a stellar solution with a fluid that has constant density, this is a solution, an exact solution of the Einstein's equations, you can find that the pressure at the center of the star is given by this expression. And the point is that this expression has a denominator that can vanish at some point. Okay? And this vanishes when the relation between mass and radius is given by this amount, which is called the Bugdal limit. This means that if you put in a given radius this amount of matter in some units, then the pressure is infinity. So this indicates that there is a maximum amount of mass you can put in a given radius. So stars cannot be arbitrarily dense. Okay, so there is a limit, and this limit follows from a very simple model. But if you consider arbitrary stellar models, simply assuming that the density is a monotonic function with a maximum at the center, this limit still applies. Okay, so this is a genetic property of general relativity. Okay, and it's already there in stellar solutions. And historically, this was a problem because at the time of Eddington, the 1920s or so, the establishment was that all the stars, those that don't have enough energy to continue radiating forever, they should shrink until reaching the size of an object like the planet Earth, or a typical planet size, okay? But Chandrasekhar in 1930 showed, combining general relativity with quantum theory, he showed that this is not really true, because there is a maximum amount of mass that a compact star can admit, in particular due to electron degeneracy pressure. The maximum mass of a star is 1.4 solar masses, okay? And if one considers even more degenerate objects, like stars supported by neutron degeneracy pressure, then Oppenheimer and Volkov in 1939 showed that this limit also applies. So if you have a star that runs out of nuclear fuel and begins contraction, electron degeneracy pressure can support the star if it is not too massive, up to 1.4 masses. If it further contracts to become a neutron star, it could have up to 2-3 solar masses. But beyond that, it is not obvious what mechanism could keep the star stable, okay? Very good. So quickly, that same year, in 1939, Oppenheimer and Snyder considered the problem of a star that simply has too much mass, is too heavy to support, that goes to be supported by neutron degeneracy pressure. So what happens if the star has too much mass and then there is no efficient mechanism to keep it stable, okay? And then they model this system as an exterior described by the Schwarzschild solution, and the interior as a homogeneous and isotropic fluid. This is a very very simplified vision of the interior of the star, that basically is like a cosmology, no? Typical homogeneous and isotropic cosmology represents the interior, and this interior is matched to the exterior, which is Schwarzschild, okay? And then they studied the time evolution of this system, and they found that the surface of the star collapses to zero radius in finite proper time, okay? But they also found that an observer from outside would never see the star collapse, that the surface of the star would remain frozen at R equal to 2n, which is the Schwarzschild radius. But what really matters is that they showed that an observer on the surface of the star, falling with the star, can go down to R equal to 0. Okay, so what this means is that the interior solution, the energy density grows without bound, so diverges with the collapse. And so the energy density is infinite, the curvatures are infinite, and the exterior up to R equal to 0 becomes the Schwarzschild solution. So this means that the Schwarzschild solution can indeed represent a physical object everywhere, not just outside the surface of a star, but also down to R equal to 0. So collapsed astrophysical objects could be represented by this line element. So at this point, it became clear that there could be these kind of objects in nature, and there was a lot of interest to explore the physics associated to them, okay? Okay, but this model was very simplified. As I said, it assumed that there was no pressure, it was spherically symmetric, and lots of simplification. So many people tried to improve the model, okay, adding, removing sphericity, or considering anisotropies, non-spherical models, but different studies showed that the conclusions of Oppenheimer and Snyder were basically robust. Okay, they didn't change. There were some important works by Rechaduri and Komar, who introduced the notion of geodesic congruences to explore the process of collapse. So they introduced some machinery that was later very fundamental to explore the most important aspects of the collapse. And they concluded that under very general conditions, so introducing the so-called energy conditions, geodesics could focus and form a singularity that was observed by Oppenheimer and Snyder. But there were some voices that did not agree with them, like Lifshitz and Kalatnikov, that they said that these focusing of geodesics were just caustics, they were not physical singularities, okay? So there was some controversy, but at the same time, Doroskevich, Seldovic, and Novikov showed that a more general collapse with non-sphericities, with perturbations, all kinds of deviations from sphericity. All these departures from the spherical idealized model, they were all radiated away, and in such a way that the conclusions of Oppenheimer and Snyder were robust. Okay, so apparently there was a lot of debate in this epoch about the actual fate of the collapse of stars. And so John Archibald Wheeler asked Roger Penrose to consider the problem, and well, you know what happened. He wrote a 2-page paper that 55 years later deserved a Nobel Prize because of this was the presentation of the singularity theorems. So Penrose, using some methodology already developed by Komar and Rechaduri, and working with inequalities in such a way that you relax a lot the conditions, you don't need to focus on specific symmetries or configurations. So in terms of these inequalities, he was able to show that gravitational collapse in general relativity under very general conditions will unavoidably lead to singularities. So the theory is plagued with this problem. Okay, it's a fundamental problem of the theory that it may lead to singularities under very natural and general conditions. Okay, for this, this is a very important result. He had to, not non-trivial, highly non-trivial, he had to introduce a new concept in physics and mathematics, the idea of trapped surface, and all the geometry associated to that. Okay, so but basically, if some energy conditions are satisfied and you have sufficiently smooth initial data, and there exists a trapped surface, then the time evolution will lead to the formation of singularities, which is interpreted in terms of incomplete geodesics. And the idea of incomplete geodesics, the relevance of the incompleteness of geodesics is described and explained in very good detail in a paper by Gerosh. I think it was from 1968, the paper. And it's very illuminating, okay? It's very transparent, because why is the notion of geodesic completeness so important? Because light rays, or in general information, propagates along null rays. And if these geodesics, these null rays, end at some point, then information is destroyed. It can be classical or quantum information, but it will be destroyed. So singularities are doing this. If null geodesics end at the singularity, then the information that is carried by this light ray is lost. And the same, something similar happens when we talk about time-like observers. If an observer, if its time-like geodesic stops at some point, so this observer is lost. So the ability to do physics is lost. So this is really a fundamental conceptual problem, okay? So this is why singularities are so undesirable, okay? So, and the fact that they can exist under very general conditions in general relativity is an important problem, okay? So, yes, we do have a problem with general relativity, and we need solutions. So, the typical, or one of the proposals is to build a better, improved theory of gravity that somehow takes into account the quantum degrees of freedom at the in the last stages of the gravitational collapse. So, matter is quantum, gravity should exhibit some quantum phenomenon behavior, and this new behavior, these new dynamics, should somehow resolve the singularities of the classical theory. Okay. Another possibility would be to consider exotic matter or exotic properties of matter fields in such a way that with standard general relativity, then you can violate the conditions of the theorems and avoid the formation of singularities. So whatever is your favorite choice, the point is that we need a solution to avoid singularities in black holes. And following the historical development, one of the first, if not the first proposal of a non-singular black hole is the so-called Bardeen black hole. This solution was presented by, this is not a solution, this is a line element, okay? A line element of this form, spherical symmetry. There is a function, f, the b is for Bardeen, and this function takes this form. So it is based on the introduction of a new scale, a new length scale, that is important at very short distances, okay? So when we're considering radii distances much larger than this scale g, then this line element boils down to the solution of Schwarzschild. It's like the Schwarzschild black hole, okay? But when we are near r equal to 0, so the denominator goes to a constant, and then this 2m divided g to the cube get combined to produce an effective cosmological constant, okay? So what this represents is an object that from outside looks like Schwarzschild, but near the center is like a de Sitter spacetime. So somehow this is represented a black hole with a de Sitter core, a nucleus that is like de Sitter. It's like a quantum gravitational vacuum energy, some kind of vacuum energy that could come from a quantum theory of gravity. Quantum vacuum could somehow modify the line element in the innermost region and solve the singularity. Okay, so this is the idea behind this type of black holes. These are the so-called non-singular black holes with the Sitter core. Okay, so these are very popular. There are many different proposals. This is the original Bardeen one. There are others that give more universality to the nucleus, because when this r goes to 0, m disappears, so the effective cosmological constant is universal, does not depend on the specific object that is producing the geometry. But there are many variations, okay? And many applications. The fundamental thing is that this is a typical mechanism. At the Sitter core is something that can avoid black hole singularities, okay? But there are other proposals. For instance, this is a phenomenological approach proposed by Visser and Simpson a few years ago, that they call black bounce. The black bounce is the idea that we have a black hole and something bounces. So what can bounce? What bounces is the radial coordinate. So they are somehow mixing the idea of wormhole with black hole, okay? And for instance, this line element is inspired by the Schwarzschild solution, simply that you are replacing r by this square root of r squared plus a squared. So when r goes to 0, this denominator is not 0, so somehow you regularize the GTT and GRR components of the metric, and most importantly, you manage to get a finite area for the two spheres. So the two spheres no longer shrink to 0 area, okay? So there is a minimum area, and this area represents the throat of a wormhole, okay? In particular, this is true if m is 0. No? If we consider a flat space, this represents the standard Ellis-Brodnikov wormhole that you can find on the Wikipedia, for instance. Okay. So, and depending on the relative size between A and M, you can have different situations. We have here, when A is 0, we have Schwarzschild. If A is smaller than 2m, we have black holes in which there is no singularity at the center, because the r equal to 0 sphere represents a non-zero surface, non-vanishing area, and therefore geodesics are well defined at that point. Okay? And then they can be extended, so the radial coordinate can go from plus infinity to minus infinity. So somehow there is like a bounce in the interior, like a wormhole inside of the black hole. Okay? So these are models that are being explored in the last years a lot, with a lot of attention. And this is very similar to the kind of objects that one finds in when the loop quantum gravity quantization techniques are applied to the interior of the Schwarzschild black hole, of the Kruskal extension of the Schwarzschild black hole. Then, when this is done, there are a few proposals for doing this. I'm just taking one example from someone that many of you know well. Javier Olmedo and Rodolfo Gambini, Pulin, and Azteca and Singh. And the result, after applying these techniques to the interior geometry, of the Schwarzschild black hole is that the typical Kruskal diagram, where here we find a singularity, is now replaced by multiple copies of this thing. So what happens when in this geometry is very similar to what we find in the black bounce case. Right? In particular, pay attention to the line element. The spherical sector has a similar structure. So it has a constant, so that when x goes to 0, the area is no longer 0, so it's finite. Okay, and then the other components are different due to the peculiarities of the particular model and the quantization procedure followed. Okay, but the broad, the most relevant aspect is that the Kruskal diagram is now changed in this way. Okay, so this is the region where we can live, we can move freely. So this represents the event horizon, and when we cross this the event horizon, we fall in the black hole region. So the black hole region is a trapped surface. So the trapped surface is a region where all geodesics, time-like and light-like geodesics, all of them, their future evolution is to fall down to this surface. Okay? In general relativity, this surface was r equal to 0, 0 area, and there was a singularity. But in this model, this is a surface that has finite area. Okay? Is what they call a transition surface, from a trapped surface to an anti-trapped surface. So this is like going from a black hole to a white hole. Okay? So in this region, everything is falling towards this transition surface, and in the other side, everything is going away. Okay? So that's the idea. So this is basically representing the bounce that Visser and Simpson were proposing. Okay, the transition from black hole to white hole is like a bounce in the radial coordinate. So the two spheres, a collapsing cell of light is reducing the area of the sphere, and after reaching the minimum area, they continues growing. Okay, but does not collapse to 0. Okay, this is the idea behind this model. And well, objects like this kind of this mechanism of this type to avoid the singularity were already obtained years before by some of us, in particular Diego Rubiera, who is here. He is responsible for this solution. But basically, just consider that the spherical sector the area is represented by this function, and it has a minimum. Okay, and this is represented here. So in this region, the solution, the geometry is basically like the Schwarzschild solution, or Reissner-Nostrom in this case. But when we are near r equal to 0, so there is this minimal surface, and then a new universe that expands on the other side. Okay, so we have different scenarios that represent non-singular black holes. We can have the Bardeen solutions with the Sitter cores, and we also have this kind of black bounce solutions. Okay, the point is that all of those solutions are static. They are idealized solutions. Okay, and it would be nice to see if it is possible to obtain any of those solutions, either the Sitter cores or black bounces, dynamically from the evolution from, for instance, the collapse of a star. Okay, so this is really a problem that is worth spending time on it. Okay, and this is why we are here. Okay, so we wanted to make some progress in this direction, and we tried to find some inspiration from of course, if you want to be original, you have to go to the origins. Okay? So we went to the Oppenheimer-Snyder model, gravitational collapse, and we have this mechanism of transition from black hole to white hole that appears in loop quantum gravity quantizations, and also in these models by Visser and all that. So could it be possible to join the two things, just to produce an object that collapses and generates a space-time like this? Well, you don't need to think too much, just to try to model a process of collapse in terms of a theory that produces bouncing cosmologies. So if we could do that, if the interior of the collapsing object is somehow similar to a homogeneous anisotropic star, like in Oppenheimer and Snyder, maybe if the dynamics is modified in such a way that the corresponding cosmology produces a cosmic bounce, the resulting black hole could be non-singular and of the black bounce type. So the ingredients are there. So we just need to, to join the points. Okay. So this is what we tried to do. Okay. And to do it, we consider, again, the recent results from loop quantum gravity, because in loop quantum cosmology there are several models. There are up to 3 models nowadays, as far as I know. You can correct me, please. That produce non-singular cosmologies in different ways. So depending on there are some ambiguities in the quantization procedure. So and depending how you proceed, you can get the traditional loop quantum cosmology model or other 2 modified alternatives. Okay, but all of them produce bouncing non-singular cosmologies. And the good thing is that these 3 families of Hamiltonian theories, the dynamics of those theories can be very well approximated by this F of R theory of gravity. Okay? Of course, I'm not an expert in loop quantum cosmology, but I have some experience with modified gravity. So this is my side. And I say, okay, very good. So we can do this, okay? And last year we managed to fit the dynamics of the 3 models with this family of Lagrangians that basically depend on 3 parameters. This one here, the combination alpha RC, and this beta, okay? Alpha RC can be determined from the theoretically, analytically, from the conditions at the bounce. This one here can be fixed by forcing general relativity at low curvatures, okay? And the only free parameter is this beta, okay? That is obtained numerically. And after the numerical analysis, we found a way to approximate this parameter using the immersive parameter and some factors that appear in the loop quantum cosmology models, okay? So basically, they are analytical, okay? But the analysis was numerical. And we reproduced very well the dynamics, the cosmic dynamics of these 3 approaches to quantum gravity. So somehow, I want to believe that maybe metric affine theories do have something to say for the effective dynamics of quantum gravity. Or maybe we are just lucky. Huh? Yes. Yes, if you look at the perturbations of these theories, even before quantization, you will find inconsistencies. So I'm not trying to say that this is the final theory that you should buy. I'm just saying that this model reproduces the homogeneous and isotropic dynamics of loop quantum cosmologies. That's all. Of course, the model, in my opinion, there is room to improve a lot this kind of model and try to address the issues with quantization and with perturbations of different kinds, classical and quantum. Okay, there is a lot to do. Okay. So the idea was to explore gravitational collapse in this family of F of R theories. But well, it's not so easy because numerical relativity methods are optimized for general relativity, not for your favorite theory of gravity. Okay. So you feel extremely frustrated by that. It's not easy to do things beyond general relativity. Okay, but luckily I have very good collaborators. 2 of them are here. And over some years, we managed to find a way to simplify the equations of this type of modified theories of gravity. So we are focusing now on F of R theories a la Palatini, okay? Not metric formulation. The Palatini framework is where metric and connection are independent. And for those theories, we found that the space of solutions of the F of R theory, coupled to some matter, is in correspondence with the space of solutions of general relativity coupled to a modified source. Okay? So this means that the modified gravity problem can be solved within general relativity with a modified matter source. Okay? And the correspondence between the modified gravity and the modified matter is very well established in these various papers. Okay? So this is the idea. in the modified gravity, we are a bit beyond f of r. So we are considering Ricci-based gravity theories. And in these Ricci-based gravity theories that depend on the metric and the connection with some matter field, a scalar field here, the dynamics, the solutions of this theory can be obtained in terms of solutions of general relativity coupled to the same scalar field, but this scalar field is coupled to another metric, h. And this h is related to this connection, okay? This gamma turns out to be the Levi-Civita connection of that h, okay? In the particular case of f of r theories, the relation is conformal, but beyond f of r, the relation is non-conformal, okay? It's more complicated, so there is more information. So now with this, as I said, we can map our modified gravity problem into a modified matter problem in general relativity, so that we can use the numerical or analytical methods of general relativity to obtain solutions, and with those solutions, construct the solutions of our theory. Okay? It doesn't mean that the solutions of this problem are the solutions of our theory. No, we use those solutions to build our solutions. Okay? The correspondence is non-trivial. There are algebraic manipulations. Okay? Very good. So we have everything ready. So now we are equipped with our f of r theory, the mapping method, and we just consider something really good, realistic, a boson star. Let's consider a boson star. Why a boson star? Because I'm not an expert on numerical relativity, but in Valencia we have a good team of experts in numerical relativity in the astronomy and astrophysics department. So they are experts in boson stars. Okay, so we joined efforts. So they are good in boson stars. We are good in modified gravity. Well, so we believe. And then we decided to work together, combining our strengths, and consider a boson star that is basically described by a complex scalar field with a typical potential with some mass. And this scalar field is of this form. Okay? Boson stars are very simple objects, but they are not too simple. Okay? They are simple in that they have a complex frequency, but just one frequency, not a sum over frequencies, only one oscillation frequency. Okay? This oscillation frequency is enough to generate the pressure that counterbalance the gravitational pull. Okay? So, and also if you have only one frequency, when you compute the modulus, the time dependence goes away. So the line element is static even though the scalar field is oscillating. Okay? So there are many advantages for this, and there are conserved quantities and all that. Okay? So, perfect. Now we can study the collapse of boson stars in the loop quantum gravity models. Well, that was our dream. Okay, that's what we wanted to do. But the application of the mapping to this model with this logarithm here makes the algebraic part unnecessarily complicated. Okay, and so we decided to simplify a little bit the model, like this. Okay, so the final picture is like this. Okay, we have a beautiful boson star problem, and then the modified gravity is an approximation, but it captures the essence of the problem. Okay, and it does capture the essence of the model because what we want are bouncing cosmologies. Okay, and this quadratic f of r theory does produce bouncing cosmologies. This is a result that was obtained here in this institute when I was a postdoc in 2009. Okay, with Carlos Barragan, who was a student doing the master thesis in the Autónoma University. So we did this analysis, and we found that the quadratic f of r theory does produce bouncing cosmologies. Algebraically, this model is much more simple than the loop quantum gravity model for the implementation of the mapping. So we decided to explore first this situation to see if it was worth considering the more complicated problem. And then we did so. We considered our f of r theory with a typical canonical scalar field. This x represents the kinetic term contracted with the metric g. Okay? And the corresponding problem in general relativity is this one referred to the metric q. Okay? And the matter Lagrangian now takes this form. The same potential, but there is an obvious nonlinearity that is inherited from the gravitational action. So the nonlinearity of the gravitational action is now somehow transferred to the matter sector, okay, with some coupling to the scalar field. So with this, considering this problem, we were able to find solutions, to explore the space of solutions for static boson stars, because we need the initial data to study the collapse. So the initial data represent a static configuration of boson stars. Okay? And here we have the typical existence curves of boson stars. And the blue line is general relativity, okay? And the other curves represent the quadratic f of r theory with plus coupling, okay? Plus there. So basically, qualitatively, it's the same. It's very difficult to distinguish one from the other. So astrophysically, this theory, for this choice of parameters, is going to produce boson stars that are basically the same as in general relativity. There are some differences, but it's not really relevant. Okay? And if we change the sign of the coupling with a minus here, then we see these differences, a new behavior there. But in the region of stability, where the solutions are stable, the solutions are basically the same as in general relativity. Okay? So we had the initial conditions, and now we can study the collapse. Okay? Before that, I just mentioned that these solutions are of three kinds. There are stable solutions and unstable solutions. Of the unstable solutions, we have two types. One represents configurations that if you leave them evolve in time, they simply disperse away. So the gas of a scalar field goes away, no? Disperses. And others are quasi-stable in the sense that they begin, for instance, in this region, and which is an unstable region with some mass, and when they evolve in time, they migrate to this region, basically to the same mass, but on the stable side. Okay? So the solutions here are stable, and beyond they are unstable. Okay? And then what we want is to explore the unstable branch, but adding a little bit an excess of matter. So adding this excess of matter, which is equivalent to multiplying the scalar field profile by 2-3%, then this moves the initial data away from the surface of initial data and forces the process of gravitational collapse. So this is how black holes are produced in general relativity when one deals with boson stars. Okay? So we did exactly the same. And this is what we found. The blue curve, again, is the result in general relativity. And this is useful to understand what's going on. So in general relativity, the scalar field at the center, so this is the maximum amplitude of the scalar field, is evolving in time. Okay? And when the collapse proceeds, the scalar field amplitude at the center grows, and at this instant of time, the apparent horizon is formed, okay? And then the scalar amplitude decays. So this is typical in general relativity. And this decay is due to the gauge choices, because you have to slice the space-time so as to avoid the center exactly, so all the mass is going beyond the domain where you can control. It's a technical detail. But this is the typical behavior in general relativity, and indicates that a black hole has been formed. Okay, or at least you have an apparent horizon. And when the coupling is negative, in our case, the evolution is very weird. The code crashes, so we get nothing. I believe this could be understood as a naked singularity, but it's a solution a branch of solutions that doesn't lead to anything interesting. And the positive coupling does behave like the typical black hole. Okay, the evolution has some small oscillation here due to to something that we don't understand. Okay, we did a lot of numerical tests to understand if there was a numerical effect, a gauge effect, but in the end it seems to be physical. There is something physical in the set of equations. There's a huge number of equations that is not easy to understand. Okay, we need to do some further analysis, but it's irrelevant. What really matters is that the evolution is like in the general relativity case. So at some point, an apparent horizon arises, and then we are forming a black hole. Okay? So very good. So we are collapsing stars and forming black holes. So we do have objects with an event horizon. And now what? Are these black holes of the type found, representing de Sitter cores, or do they look like black bounces? If they were de Sitter cores, we should look at the GTT component and see if it looks like, if this component of the metric looks like a de Sitter line element, no? This the de Sitter function, if it has this dependence with the radius. And if we were looking at black bounces, we should pay attention to the angular sector and look for minima in the area of the two spheres. Okay, so we have these two options. We don't observe this. If you want to know more about this, you can have a look at this paper by Saulo Carneiro and Giulio Fabris. It's a very nice analytical model. It's interesting. I believe it has instabilities, but haven't yet done the calculations. But we are, I just advanced that we are in this sector. Okay, we are going to observe a minimum in the area function. Okay, and this minimum is represented by our numerical results in this plot. The blue curve represents the emergence of a minimum in the G theta theta component. Okay, for some time there are no minima. Okay, so the spherical sector is monotonic, as usual, as our intuition tells us that it should be, from R to infinity to R equal to 0. But at some point, the spherical sector develops an extremum. The size of this extremum grows and then decays slowly. Somehow it stabilizes. It enters in some domain that is more or less stable. This happens, this minimum arises before the emergence of the apparent horizon. Okay? But in the end, it is hidden by the event horizon. Okay? So what this means is that the emergence of this minimal surface cannot be observed from outside. Okay? So cosmic censorship is acting here. Okay? This was a surprise. We weren't planning anything of this. Okay? This is a result of the numerical evolution. Okay? And then let me show you what happens in the interior geometry. Okay? This is a Euclidean embedding of the interior geometry. Okay? If you have a flat Minkowski spacetime, so this should be like a cone. The center, R equal to 0, is here at the tip of the cone, and then different spheres or different radii are represented by circumferences. Okay? Here. Well, it's difficult to project from here, but you understand the idea, right? Okay. So, and this is representing the geometry inside the star. Okay, so matter will, when we start the evolution, the numerical evolution, matter will begin to fall to the center, and energy density will begin to accumulate at the center. So the energy density is growing at the center, okay, or around the center. And let me see if it works. Yes, it's working. And this is what we observe. Pay attention to this region here, where the energy density is accumulating. The minimum appears, and then a sphere begins to grow. Okay? So what this means is that the center of the black hole, because now it's a black hole, there is an event horizon, or an apparent horizon, the center is accumulating energy. And when enough energy is accumulated in that small region, then a process of an stretching, an expansion of the space-time is taking place in that region. Okay? So this is like an explosion, but since we have an event horizon, the explosion, the matter cannot explode backwards outside of the black hole. It must explode somehow forward, whatever it means. And what it means is that this region of space-time is stretching to generate a new bubble, a new universe. Okay? And by generating this new universe, then the matter that was concentrated at the center can now expand forward in time. Okay, so this is what we call the birth of a baby universe by the collapse of a black hole. Okay, and this is what happens due to the emergence of this bouncing cosmology, effective bouncing cosmology in the interior. We were not modeling a bouncing cosmology. We were just using describing a collapsing star, okay? But the evolution is naturally and automatically moving in that direction, okay? So this is the 3 snapshots of the process. So initially we had the Euclidean geometry, then the minimum develops, and this sphere begins to grow, and the growth is so fast and so powerful that soon we lose control on the numerical, and this is why it looks like flat, because the sphere is huge, okay? And the rate of, well, actually there is something to say about this. The size of the throat is changing with time. If you remember, initially it was growing, it was bigger, so this means that the throat was broad, and then is somehow contracting, and it is contracting. Why? Well, the first question is why it is not closed, okay? The point is that this throat is not closed because in boson stars, in general relativity, when the boson star collapses, approximately 95% of the mass falls inside the black hole, and the other 5% forms a cloud around the black hole. So this is a hairy black hole, okay? So the same cloud of scalar matter is formed in our case, but this cloud is slowly leaking in through the event horizon and falling down. So it is this energy density that is falling down slowly that keeps the throat open, okay? And at some point in the future, at very, very late times, we suspect that the energy density will have been absorbed completely, and then the throat, there will be no energy density at the throat, and then it will close. So effectively separating the 2 spacetimes, the mother spacetime and the baby universe, okay? Okay, so the rate of growth of this bubble is represented here in time. This is logarithmic scale. So what this shows is that the growth of this bubble is exponential. So this has all the ingredients of a typical inflationary model. So inflation is taking place here. This is what we understand by inflation. You know, typical models of inflation assume a very inhomogeneous spacetime, but in some patch, the inflationary mechanism started, and this patch stretched to astrophysical scales. So this is what is happening here. The region near the center of the black hole is stretching and forming a new universe. And that stretching is exponentially fast. Okay, and it's represented here. Okay, so this is the idea that in general relativity, gravitational collapse leads to singularities under very general conditions. Okay, but beyond GR, there is hope. Okay, the collapse may still yield sensible results, sensible outcomes, and you don't need to look for specific solutions. We have just found that the black bounce idea, or the transition surface predicted by the loop quantum gravity models can arise naturally, okay? So, and this is just a model, a very simple model, okay? And it's showing that with initial regular data, very simple data that correspond to typical boson stars, the time evolution is leading to the formation of a black hole and a baby universe in the interior, okay? So, if we believe that the Schwarzschild solution is valid up to r equal to 0 due to the time evolution that Oppenheimer and Snyder showed, they did the calculation, okay? Now, the validity of these baby universes is also supported by this numerical analysis, okay? So, and we believe that this should be the picture for gravitational collapse in not just the FOFAR theories, the quadratic model, or the loop quantum cosmology models that I showed. In any model that has associated bouncing cosmologies, gravitational collapse is likely to proceed like this. Okay, this should be a very generic mechanism. Okay, this is still to do. Okay, there is no, as far as I know, this is the only complete analysis of this process of collapse. But if I'm sure that when in the future we will explore other scenarios with other theories of gravity and other dynamics, and I'm convinced that this will be generic. And well, from this we can speculate. No? We can think that maybe our universe, the inflationary epoch that we suspect that existed in the past, could be similar to what happens here. So maybe we are part of our universe is the result of an object that collapsed in the past, okay, following this mechanism. This is one speculative idea. It's possible. Another possibility, another thing that is worth exploring is what happens if this kind of geometries could exist, okay, without horizons. Okay? We have seen that these objects have an event horizon and they are dynamical and representing a growing universe. But does it make sense to think about this kind of geometries? Because typically when we think about wormholes, we think about two symmetric universes, or at least two infinite universes. One on one side, one on the other, and the throat is in the middle, okay? And also, we are used to characterize wormholes by a local characteristic that is the wormhole throat, the minimum in the two spheres. But wormholes are topological entities, and it is not possible, and topology is about the globality. And we are identifying the existence of wormholes by something local, like the minimum in the throat. So it is a good exercise to consider this as a counterexample for these wormholes. So here we have a local minimum in the two spheres, okay? But maybe there could exist scenarios where there is a minimal sphere and then an internal bubble, not an infinite universe. Okay, so could this be observable? What could be the signatures of these kind of objects? And yes, there are observable effects, in particular regarding the echoes of gravitational waves. And the echoes of gravitational waves in these kind of objects are completely different from what we expect from a typical Einstein-Rosen wormhole. In the Einstein-Rosen wormhole, this is the Ellis wormhole. We would find some echoes due to the presence of this peak here. This is the profile of the gravitational waves of an Ellis wormhole. But in our case, due to the existence of an internal bubble, we could have trapped modes that could be oscillating here and leaking energy from outside. So and this would produce a series of echoes, very characteristic echoes, whose properties depend crucially on the height of this barrier and the width of basically the radius of the bubble inside. Okay, so an infinite bubble, that would be a typical wormhole connecting two universes, would give a gravitational wave profile like this, but a finite bubble gives something like this. They are very different. Okay, so there are this analysis first points out that there are alternatives to the singular end of gravitational collapse, and second, that there could be more exotic compact objects whose gravitational wave properties would be very characteristic. Okay, and that's it. So this is the summary here. Thank you so much.
Okay, time for question. Gianluca. Mm-hmm.
So the problem of a singularity in general is not just to find bouncing solutions, but to show that these solutions are typical in a given theory. And nowadays there are theorems that even are independent of the dynamics and that show that, for instance, the Big Bang is a very typical singularity at the classical level. I would suspect that the Borde-Guth-Vilenkin theorem would apply also to the interior of your solutions, which would basically show that they are not as typical as you hope.
Well, thank you for the comment. I don't know the details of this theorem and the potential implications, but I would say that for But this mechanism should be as general or as generic as the one associated with the de Sitter cores. Simply that this allows for a dynamical analysis. Probably the de Sitter cores are not so stable as for many reasons, but this should be a generic, in my view, should be quite generic. This type of solutions. So, but this is just my view. It's probably completely different from yours.
Okay, any more question? Yeah.
So I have a question whether you have checked that the geometry is singular or non-singular, because you can, maybe you could try sending the geodesics from the null geodesics from the surface, let's say, of the collapsing matter, and check whether they are.
So technically, the geometry as a whole, I would say, is singular. Thinking in this growing bubble, you know, not just if you focus on the extreme of the bubble, that region, in my opinion, that should be singular. Okay. Or even I can confirm that it's singular, because the f of r theory that we are looking at is related with general relativity, where we do the calculations by a conformal transformation, and the object that we find in general relativity is a typical black hole, so it has a singularity at r equal to 0. So the conformal transformation is not going to change that. So that point will be singular. Okay. Now the situation is the nature of the singularity of the space-time in the dynamical process. When the bubble is expanding, this expansion is superluminal. So there is no time, there is no geodesic that can move faster than the expansion of the universe. So any light ray emitted after this process is starting will never be able to reach the other side of the bubble. Okay, so in practical terms, that region is like a new boundary of the universe, at least on the time scales that we are working. Of course, we would need a complete time evolution to infinite time in order to see what happens with this bubble. Okay, if the expansion is changing, or there is some transition, because as I mentioned before, I was forcing the analogy with inflation, and inflation we know that it has an end, and after inflation we have preheating and all those processes. Okay, so if that happens here, then obviously these geodesics at some point will be able to reach the other side of the bubble and reach to r equal to 0. Okay, and then you could have the problems of singularities. Could this be avoidable in other models? Yes. I mean, this limitation. Well, I don't know. I don't know. Okay. I know that this is a limitation of the f of r theories that we are considering. Okay. They have other limitations. For instance, if you consider this bouncing cosmology at the classical level, if you consider inhomogeneous or anisotropic perturbations, the bounce will not be well behaved. Okay, but you can consider other extensions of the Ricci-based family beyond f of r, where the bounce is regular and even robust in anisotropic and inhomogeneous cases. Okay, so the f of r is just a nice illustration that simplifies many things, allows to do the calculations, okay, and gives you green light to continue exploring other theories or more complex scenarios. Okay, so I think
Yeah, because what I understood, you based your theory, you were inspired by loop quantum cosmology and related theories. So, but the recent models of dust loop quantum cosmology, they were studied in the context of the Oppenheimer-Snyder scenario, and the geometry turned out to be singular in the vacuum region, in the sense that the whole geometry resembles the Reisner-Nordstrom solution in classical GR, so you have the singularity at x radial coordinate is equal to 0. So yeah, this was my curiosity whether this should stay the same actually in your model. And in general, it would be interesting to see the conformal diagram with the model you are presenting.
Yes, preparing this talk, I found those works. In particular, I haven't read the details, but now I'm aware that they exist. So there were dynamical solutions in loop quantum gravity in this context. And I didn't know they were singular. I thought they were somehow avoiding the singularity. And the other thing was, did you mention it at the end? The conformal, yes, this is another thing that we haven't done yet. No, the conformal diagram of the evolution process, I haven't thought about it. Yes. But I should do it. Thank you.
Okay, time for one more question. No? Okay, thank you, Gonzalo, for your talk. Well, thank you very much for your attendance, and next seminar will be announced probably in 2 weeks, okay? Thank you.